Good afternoon, everyone. So maybe before I start, I'll just want to know, like, any of you are working on AIML? No? Okay. So I'll start with the agenda. That we need the first. We'll start with we would like to know what is the trustworthiness of the prediction, and then we will quantify the uncertainty with each of the predictions, and then Chand will help me in a demo for the hard drive failure prediction, and the last is the need of it. So let's begin with the classical machine learning approach. So I have just given an example here for a binary classification that we have been provided with the input data set. So if you see there that till here is the historical data set, and the next day you'll get a new X variable, and the machine learning task is to provide the label of this one. That is completely fine. So what we do in a classical machine learning, that we try to create a mapping function with all the historical data of X, which are the parameters, and then we try to predict this Y. But this all is based on the historical data. But and if we see this YN, the new one, right? So this data, this new data set, it has never seen this function, the machine learning model, right? So now when we are ready with the performance, when we are ready with the prediction model, then we say that okay, my model is like 98% accurate, or maybe like 99.99% accurate, right? But what about the accuracy and the confidence of prediction for the yn, which is the yn plus 1? So we don't know about it, right? So the whole goal of this talk is to let us understand what will be the confidence of the point prediction. So most of the prediction model, they give you just the prediction but not the confidence. With what confidence you are saying that the new prediction will be maybe 98 or 99%, right? So the need of the R is to get the confidence of the prediction and the informativeness of the each new data point. That is the Y, the last one. Okay. So how do we quantify this uncertainty? So to quantify the uncertainty, we need to understand what are the sources of uncertainty, and then we need to handle each of them. Okay, so what we see in the green box, that is the complete data science life cycle. So we begin with the data set, we clean it, then we keep on then we create a model, then we have the point prediction. But if you see from A to D, they all have a point of uncertainty in each of them. So starting from the data collection to the model to the model creation, we have this uncertainty in them. So we try to take a union of all of them, and finally we have prediction uncertainty. But here in this talk, I'll be only covering the model uncertainty. So historically, people have already worked on this to estimate the model uncertainty, the confidence interval, prediction confidence. Okay, but this approach is also not a new. This is already people are doing in 1960s based on the algorithmic theory, and the thing is it's based on a robust mathematical foundation, and this has been this has been validated. Okay, so the problem with finding the algorithmic randomness is it's non-computable. So what we try to do is we try to approximate the confidence. So now I'll just introduce this conformal prediction framework, which will give you the confidence of each new predictions. So basically, this is a learning framework. I'm not trying to sell a new machine learning algorithm, and you can put it like a wrapper around it, and you will get what you were getting with your prediction model, like your prediction may be like pass, fail, or the regression. Okay, but by wrapping this learning framework, you will get the confidence and the credibility, which I will explain the need of it. So the framework is based on algorithmic theory of randomness, hypothesis testing, and there's one more thing, like we will decide the significance level. Significance level is about like how much tolerance, how much you can tolerate the error level. So that we will define it. And there's a assumption for this, that the data set which we'll be using, it should be exchangeable. So basically exchangeability means that if we have a data sequence of x1 to xn, of this initial sequence should be same if we interchange the sequence. So the joint probability distribution should be same. Now how we are going to test the exchangeability? In my case, I have used plugin martingales for testing the exchangeability. And like if you see on the left hand side the exchangeable data, and if you see, like it is always less than 1. So if the values are always less than 1, this means that it has passed the test of exchangeability. But you see the figure number 3, and around 40 to 45, this is keep on increasing, right, more than 1, so it fails. So this data set we cannot use for conformal prediction approach. Now this is the framework what we'll be using. So we start with the nonconformity measure, which is based on the randomness theory. Then we will use hypothesis testing, and we will find the p-value. And if you see the third prediction set, so this is based on the significance level. And finally we'll get the inference, that is the confidence and the credibility. So like let's start with like what is nonconformity. So nonconformity is that when we get the label, the new data point, so we need to understand that the new data point, how strange is from the existing data set, that is the historical data set. And here as an example, I have used a very simple classification algorithm, that is a k nearest neighbor, where I have used k equal to 1. So I'll just move to next slide. Okay, so let's try to understand the whole steps using a problem statement where we want to predict whether the disk is going to fail or not. So if we see that we have this 2 red disks and the 2 green. So here my assumption is that the red one are the failed and the green one are the normal disks, right? So our initial task is that the middle disk, which is the gray color, we need to say according to my prediction algorithm that whether this is going to fail or not, right? So if you see the numbers associated with them, so those are the Euclidean distance, and those are the steps when we do k nearest neighbor algorithms. Now if you see the slide the first step is finding the nonconformity measure. So according to our hypothesis testing, we will first assume that this drive is going to fail initial, okay, and we will also calculate that this drive is pass. So this is our hypothesis. So now I'll just help calculate the first one, that the alpha I is the nonconformity score of the first drive. Okay, so this nonconformity score we have to design. So like for if we are using a random forest algorithm, so there we have to design the non-conformity score based on the number of votes it is getting. So, so here you can design, you can choose any of your favorite algorithm and you design your non-conformity score, and then you calculate the alpha values. So if you see here, like distance of similar and ij, right? So that will come to 3, right? This one, and similar. So similar is dy similar is 3, right? This one, the same and the same and near is 3, and for this one, and this one will be different and near, so it will be 8, so 3 by 8. Similarly for b, we have this b where, yeah, this one, so it will be 4 by 9 this side. So this way we calculate the non-conformity scores for all of the data point. So we are just trying to understand like how this A is different from all of them, right? And in the similar way we will calculate for this one also, assuming that this is of the label failed, right? So in the same way we calculate the non-conformity score, right? Assuming that this is pass. So we will get a table like this, which we call like the p-value and the prediction. So like this will be the p-value calculation, which is like over here it is your alpha of y. This one, this was y, right? So for the same disk, we have calculated 2 different p-values, right? So we have like this number is 0.5, what we have got it here, right? So we need to have like greater than or equal to. So we have just 2 values, right? 2 values, this one. So we also include this one. So it will be total 3, right? And total number of data point is 5. So it will be 3 by 5. Similarly, we calculate for the normal disks, and like lower the p-value, higher will be the non-conformity scores, and the confidence will, the credibility is the maximum p-value. So our maximum p-value is 0.6. So this is the credibility, and confidence is 1 minus second p-max. So here second p-max is 0.4. So we have like credibility, confidence is 0.6, right? So like from here we can infer that the like if we just assume that we have not used a conformal framework, so confidence is like with 60% I'm confident for this new label that this drive is going to fail, and the credibility is like credibility will talk about this. Credibility will talk about the data, like the quality of the data, like what is the data. So from the credibility we can infer whether the data needs to be do we need to give a rethinking. Okay, so like what I explained was conformal prediction, but it is computationally very expensive, right? So we try to see some method using which it can be computationally inefficient. So informal conformal prediction is one such approach. So what we do in ICP is that this whole data set we distribute into training, calibration and the test. So according to that we calculate the p-values, right? And another is the cross conformal prediction, where we split the data into k sets. So all the variants, they all depend all depend on how we are splitting the whole data set. So that's one of the thing. Okay, now I will hand over to Jan for explaining the applications of it.
Thanks, Rahul. Hello. Hi. I know it's difficult post-lunch. You know, it's very difficult for me to stand with him there post-lunch. By the way, I didn't have my lunch. Yeah. Thanks for being here. It was first time for us in US, both of us. To be frank, we didn't see anything here. We just came for the conference. Okay, I don't take much time. Just please don't be angry on me. I'll just wind it up. Much of the things are already covered by my friend. Okay, applications. We could already see that this particular framework has been applied to the industries like health science and drug manufacturing, but we couldn't find much of the work especially in storage industry. So if our talk is going to be confined to the storage, so we just had a demo. I mean, we have implemented this in our environment in the storage industry. So if we speak about the use case in the storage industry, it can be many, but a couple of more important things can be a hardware failure prediction, where we have a disk drive failure prediction, and anomaly detection. That's a time series one. So we all know how important is a hard drive failure prediction in a data center. So it can also be, this framework can also be applicable in a core machine learning approach also, like a feature selection, where we select which features we have to use for the prediction algorithms, and then in order to assess the quality of a prediction. So again, we're going to talk only about the storage industry, and especially here we're going to talk about the hardware failure prediction. So this is what we implemented it. I'm sorry if you're expecting something else. Okay, so what we did is, so from here, I'll just walk you through the slides of particular demo. The way we implemented it, a demo, we just took the screenshot, we couldn't make a video. So we took a data set. It's an open source data set which is available through Blackblaze. Blackblaze is a data storage provider. So we took a latest data set, Q2, 2019 Q2, and then we started cleaning the data. So it's a normal machine learning stuff, what we did. From there, cleaning, of course, we removed all the NaN values, and then the most important thing is feature selection. So the data set which was thrown by the Blackblaze has 100 plus features, which are smart value parameters and few of the IO parameters. We had to find out the features which are important. Of course, we did a feature selection engineering, and then we took out 7 to 8 features just from that feature selection. After that, we have applied this conformal prediction framework on top of the data set. Underlying this conformal prediction framework is using a KNN, K nearest neighbor classifier. So we have actually wrote a small package on PyPy. If you want to try it, you can just try it out, and then you can always shoot an email to us if you feel anything has to be added. If something broke, you can always call us. And we'll just go for the interpretation of results, how the results actually looks like. It's not just a prediction what we do. We just tag something called confidence and credibility of that. And we rank the predictions. I will just walk through how it looks. So this is a sample data set. We took it from Blackblaze. If you see, it had a lot of features. So the right hand side, blue colored column highlighted are features. So if you can see the orange one highlighted, is it orange? Am I bad at color?
No,
I think it's orange. Yeah. Okay. So this is the status of the disk which the data set has. 1 represents the failed, and 0 represents the normal disk. So these are data set which we took, and then we just use the pandas and to do the normal cleaning, data cleaning. So these are the head of the data set, how it looks like in the bottom. So we have installed the package. These is available in PyPy. So we have installed it, and then we have passed the data set to this particular package. Yeah. So what this package, as my friend was explaining, so what it does is the conformal prediction framework. So it is basically a hypothesis testing. It is going to assume first that basically here our goal is to identify if the drive is going to fail or not. It's a classification problem, 1 or 0. So it is going to assume that first it's going to fail, and then again it's going to assume that it's going to be normal. So basically we have 2 probabilities: being normal, being failed. That's why you call something called p-value, the probability value. We can see in the table down there, the first new data point, it is going to assume that it's going to fail. That's where the first column is p failed. That's a probability value of being failed, and it's going to calculate the probability value. That's a nonconformity measure, what he was explaining about the equality and distance, how it calculates. And then it's going to assume now it has normal disk, and it's going to calculate the probability value, its p-value. You can see the second and third columns, p failed and p normal, are probability values of that particular new disk is going to be failed or normal. Depending on this p-values, we can say whichever p-value is maximum out of that failed and p normal, two p-values, it's going to mark the drive as that particular status. So here in this case, the failed has more probability, 49%, so it marked the status as failed. So we have, so this particular framework will give an extra information, that is confidence and credibility. To this particular tag, it's going to give you how much confident am I going to be when I'm going to say that the particular drive is going to be failed. So we are not just simply telling that the drive is failed. So including that, along with that, we're going to tell that how confident we are. So this makes sense, especially when we are dealing with a like data center problem. It can help us efficiently manage the inventory management. So if we see this, there's an example how it looks like. So say we have an algorithm, prediction algorithm, so where we want to predict if the drive is going to fail in next n days. So n is the forecast duration. It can be an example, it can be 5 days or 10 days. So in my data center, for example, I have vast number of disk drives. So if I do a normal prediction, it's going to give me, for example, it's going to give me 10 drives are going to fail in next 10 days. Say my inventory has only 3 drives as a spare drives. Now, by using this confidence and credibility method, and I rank it with the confidence, now the particular lab hardware team can go and do a powerful action, insightful action on those which are really, where I'm really confident that it's going to fail. I don't have to randomly go and pick it up. I know that the first row there, it is confident of 95%, I'm confident that it's going to fail for the first disk serial number. Second one, I'm 91% confident. So in this way, I know that I can take an action on particular disk drive because my framework is telling me that I'm 95% confident on the prediction. So this is how the output looks like. We just plotted the same in the to visualize it how it looks like. Confidence and credibility. If you see the right hand side top, yeah. So my new data labels I predicted has to be on the, if it is on the right hand side top, it means that it has more confidence and more credibility. We can live with less credibility, but we always need a more confidence in order to take an action. So to an end user, if we have to give a visual interpretation of how it looks like, we just placed it. So this is how it can be for next, for example, I have to forecast for next 5 days. So these are the table looks like. It is giving this disk serial number and what is the confidence that it's going to tell that this particular disk is going to fail. I'm giving a confidence and credibility. Credibility is how good is my data used for this prediction. So this way we know how confident we are when we are telling that particular drive is going to fail. So am I good? Okay.
Any questions so far?
Yeah.
Okay, please go ahead. Come. Yeah, you.
Okay, yeah. There's sort of the costs are kind of asymmetric about getting a prediction wrong. And a false positive, and you pull the drive out, you lose some useful extended value of the drive. A false negative, you don't pull the drive out. And, sorry, I made it backward. But anyway, you don't pull a drive that does end up failing. The cost on that in a huge data center is actually quite low because you've got in all that built-in failover and redundancy. In fact, it's fairly frequent that the policy is the drive dies, you leave it in place. So is there a way to somehow attach costs in here on this to kind of make your predictions more useful?
So maybe like we were under the assumptions that we are dealing with a very big data center where although like the failure rate is like less than 1%, right?
Sorry, less than how many percent?
Less than 1%, right? There may be inventory problem, right? So if they have all the details here, they can make a judicious judgment.
Okay.
But still you can have all the confusion matrix, false positive, precision, recall, still you can have it. This is just like a wrapper around existing algorithm. Yeah, please.
For the data you have displayed there, the drive, first drive and the third drive,
Please.
That's still in the sequence?
These two?
No, the page that you that up.
Please go back.
This one?
That one, yeah.
Yeah.
This one?
There's the disk failure forecast. Yeah, those, the first drive and the third drive. Could you step us through your decision process on those? Because the first drive has a high confidence and a medium credibility, and the third drive has a slightly lower confidence and a higher credibility, or maybe the second and the third. You know, would you fail all of those? Would you pull all of those, or?
So the ranking, yeah. So the ranking is based on confidence. So the ranking there is based on confidence. Credibility is just to tell that how good the data we used for this particular new data prediction. So basically, for your question, if how we decide that this particular drive is going to fail, like.
Yeah, are you going to pull that drive and say it's going to fail, or not, based on these numbers?
We are going to pull it out.
So where's your cutoff there? Are you pulling out all of those?
No, based on the ranking and based on the need.
So what I'm saying is you've got a confidence ranking. What do you do with the credibility ranking?
Credibility is for the, again it's like a life cycle. Again it will loop back to the, how we are processing the data. So it's for that part.
Okay, but your decision is based entirely on the confidence.
Confidence.
Okay, regardless of the credibility.
Right.
So what does the credibility tell us?
Credibility will tell about the informativeness of the data. Like how informative is the data. Suppose that if we are pulling the data, right, it might be having some noise, right? If the data is not cleaned properly, or maybe the imputation which we have done, it is not proper. So that it will help you identify it. And then you can again go back and tune how you are collecting the data.
I see. So that's the action you would take.
That's the action. Okay, welcome.
You know about the confusion matrix, right?
Yeah, right.
Which says about accuracy and precision.
Right.
So have you compared your accuracy and precision of your algorithm with this data and how it correlates?
No, we have not compared. I'll tell you like how it is different from, for example, it's a regression problem, right? You do a R square. MAP, right? You do everything. If it's a classification, you do a confusion matrix, right? Precision, recall, ROC, everything you do, right? But now, can you tell me, like, do you do this one for the new, just a second, do you do this one for a new data point, or you do for the model? In real,
So end of the day, this is a classification problem.
right,
You are not failing.
right,
It can be done even by a logistic regression,
yeah,
right?
yeah,
But you use the KNN algorithm.
yeah,
fine. But each algorithm, if you have used scikit-learn or something, you can calculate that confusion matrix at the end of the algorithm, a clear formula what is given.
right.
So my question is like how it is aligning with this. Like have you tried comparing the precision and accuracy values to your confidence and credibility, so that it's like a cross-checking mechanism so that your process is correct.
Okay.
So have you correlated those things?
Okay, let me try to bridge the idea. Okay, so I'll just again go back to the previous slides, okay, where I was talking about that, can I just please go back, the first one? Yeah, just come here. Yeah, okay, so see, when you do your model performance evaluation, right, so you do till here, which is your historical data, right? And assuming that you have never seen this data, right? Am I correct? Okay. Now, when you create a, if you assume that this is a regression problem, right? Then we do a R square, right? So this R square will tell you the, accuracy of this model, right? Train and test. But R square will never, and this is the place where this conformal framework came into the picture. That now what about this data point, right? What is the, how the model is performing with new data point, which is I never seen it, right? Is this making sense?
So you are giving the confidence for the new data, not for the model.
No.
So that's what my
Okay. That's why I told you that you can use any of the machine learning method here, and you can use conformal prediction as a wrapper around it. So this wrapper will give you the confidence and credibility, and this algorithm will give you the prediction, like a regression, some data points, and for the classification it will give you like pass fail or labels it will give you. So that's the reason I told earlier that you can use here your favorite algorithm. So it is up to the data scientist to figure it out which model is performing best for him.
It's not a model judgment. It's not a hyperparameter tuning type of thing. It is based on once you have this model, assuming this model is 1% accurate,
Right.
what is the confidence level of prediction based on this model?
Right.
So for example, you can use the probability given by the model. Okay. So you're using the p-score. Is this a little null hypothesis type of thing?
Yeah, it's like a hypothesis testing. So where we assume that the same label, this particular label is like label A and label B at the same time, and we calculate it.
Could you talk about which model you use for your application? Is it a reinforced or is it potential or is it something?
Sorry, please come again.
Could you discuss what type of model you use for your application that is okay and
It's a K nearest neighbor classifier. Nearest neighbor classifier. Yeah, I just tried to make it more simple. So we were. Okay. Actually, we were using like a Mondrian forest classifier for this one, like in a lab.
Okay, so conclusions. Of course, we do have challenges, like a couple of people are asking questions. So challenges, calculating the non-conformity score, obviously it's a challenge because we need to calculate the efficiency and validity. Validity is, here we need to stress one point. When we have opted for the conformal prediction, we are actually compromising in getting a point prediction because we are not getting a point prediction here. Basically, the conformal prediction is something we get a set prediction. It gives a prediction in a set. So, for example, if I'm saying we don't want to give a tutorial on conformal prediction, so we didn't include this stuff. So basically, it's going to give a set. That means if, for example, my problem is a binary classification, it won't give a point prediction like it's going to be 1 or 0. It can give a set, like it can be like 1 and 0 both. We need to get the compromise. We need to have that compromise if we have to switch to this, because we don't get a point prediction here. It's a set prediction. It gives a set. If, for example, it's a regression problem, it will give a set. If the set interval is very big, that means it is less informative and more reliable. If the set prediction is very less, it is very good informative, but it's less reliable. So there is a trade-off if you want to switch to this. So an application in time series, it's a challenge because assumption of this conformal prediction framework is the data should be exchangeable. So we know that time series, when we use a time series data, we have a difficulty in exchangeability there. We shuffle that, it breaks exchangeability. So we need to bring the data to the weak exchangeability and then apply the framework on top of it. There is always a challenge in that. And summary. So the main intention, as I said, it's not to sell the new learning algorithm. It's just to give a new learning framework which can be wrapped on, can be used with any of your existing model. So that's also.
So just to answer, reiterate your question, like, so this is what we conclude.
It also depends on how you design your model.
Exactly.
If you overfit it, it's not going to definitely predict the results properly.
Exactly.
Also, if it is underfitting with higher bias,
right.
there also.
So yeah, the framework has nothing to do with the model. So model is it's end of the day we can decide what we have to use it. So this is just a wrapper on top of it.
Yeah, and there's one more thing, like see, prediction means that we are dealing with uncertainty. Like if we are not certain, that's why we are trying to predict it, right? And that is the whole motive of like quantifying it, how uncertain it is. That's all.
Okay, so a bunch of people who already uses it, like drug manufacturers, to know that new drug is toxic or not. So it just don't give the point prediction like it's toxic or not. It just tells that how confident I am to predict that it's toxic or not. So it is used in health sciences. Many of the use cases like cancer, detecting a cancer cells, and a couple of other things. Yeah, even insurance domain uses it. So these are references. I think we're done.
Yeah, any other question so far? No?
Thank you.
Thank you very much.